Welcome back, and we're continuing our look at energetics and in particular thermochemical equations and exo and endo processes. We've talked a lot about exothermic and endothermic reactions, their enthalpy diagrams, and looking at how we can calculate the amount of heat given off by a reaction using Q equals MCAT. Now we're going to look at putting that together with experimental data, what that means for things like combustion reactions, and how we represent this in chemistry through thermochemical equations. So obviously one of the most common exothermic reactions that we come into contact with in our society are combustion reactions. So in order for a fuel to undergo combustion, there are three things that we require. One is the fuel, which is usually some form of hydrocarbon or fossil fuel. Okay, the other is oxygen. Things do not burn without oxygen, so they need oxygen to be present in the form of oxygen gas. Okay, so O2. And we need energy to initiate the reaction. Combustion reactions do have a activation energy that we need to be able to overcome. Okay, so if we think about activation energy here, so they need a spark source. We need to ignite them. They need ignition to be able to go. So we need to get over the activation energy barrier in order for the combustion reaction to occur. Okay, so combustion is an oxidation process, which we will revisit when we do redox chemistry. Okay, but this means that the carbon is oxidized, oxygen is added, okay, and the oxygen is reduced. This will make a little bit more sense as we move on through redox chemistry later this year. But in standard combustion reactions, water will always be present as H2O gas, okay? Because when we burn things, we are burning things at over 100 degrees C. When we write a thermochemical equation, though, which is the equation that shows us how much energy was given out for that reaction, it's as a liquid, because if you think about it, when the reaction goes and gives off its energy, okay, so from A to B plus water, okay, it's going to give out energy. What is actually happening is the water absorbs some of that energy and turns into a gas. When we are talking about the energy that is being put out by the fuel, we want the total amount of energy. We don't want the total amount of energy less what's been absorbed by the water to undergo its phase change. So what we do is we talk about a thermochemical reaction where the water remains as a liquid. Okay, so therefore it has not absorbed energy to turn into a gas. So the value of energy released from the fuel does not account for the energy that would be absorbed from the change of state. Okay, and this is something to look out for when you are comparing theoretical values versus experimental values, because when we measure it experimentally, this is going to happen. Okay, so that can be one of the discrepancies that we see experimentally. So just a bit of review on balancing combustion equations. Okay, so this mnemonic here, CHOS, chose, okay, is how we always go about it. We balance carbon, then hydrogen, oxygen, and then we put in our states. Okay, so combustion is complete when it occurs in excess oxygen. Okay, so this means that all carbon will be converted to CO2, so the products will only ever be CO2 gas. And as before we said, H2O liquid, okay, when it's thermochemical. So the incomplete combustion reactions can vary, and they give us a variety, the carbon monoxide, carbon solid or soot, okay, and CO2. So you're not going to be asked to balance a combustion equation unless they give you what the products are specifically. Okay, they're not just going to say write an equation for the incomplete combustion of blah. Okay, they're going to have to say write the equation for the incomplete combustion giving carbon monoxide and water as the products. Okay, so it can be carbon monoxide, carbon solid, which is soot, water, and we can even get some CO2 depending on how incomplete the combustion is. Okay, so this is an example of a combustion equation for the combustion of ethane, C2H4, which is one of our hydrocarbon fuels. It is a gas because gases are what burn. Okay, to produce carbon monoxide is given by the equation C2H4 plus 2O2 goes to carbon monoxide and H2O. Okay, you can't balance this unless you know the exact products that they're asking you to do. So I want you to pause this video and have a go at balancing each one of these equations. Once you've balanced them, come back and check the answers. Well, hopefully you got the same as what I did here. These were a couple of tricky ones. So with the hexane here, we needed to double our coefficients in order to make sure that everything balanced. Okay, so initially you would have had 1, and then you would have gotten 7H2O, and then you needed to double everything to make them whole numbers. With methanol, you need to make sure that you don't forget the fact that we have an oxygen in here and a hydrogen when we come to balancing it. And then, of course, the incomplete combustion of methanol, we were just going to carbon monoxide, not carbon dioxide. So when we talk about heat of combustion, we are talking about the enthalpy of the reaction for combustion. So we give it a little subscript C. So we're talking about delta HC. This is the amount of heat produced by the combustion of 1 mole of the fuel. Okay, so if we're talking about methane, which is CH4, 1 mole of that fuel is going to be 16 grams of fuel. Okay, is going to give rise to 890 kilojoules of energy, because we get 890 kilojoules per mole. Okay, so this is how much we get from burning 16 grams of methanol. Okay, so it's for 1 mole of fuel, and energy is in kilojoules. And this gives you some idea of the different types of energy that we see giving out. Remembering here that this negative for enthalpy is indicating that it is, of course, an exothermic reaction. So heat of combustion is the amount of heat produced by the combustion of 1 mole of fuel. So it's the same as the enthalpy value written for a chemical equation. Okay, so when we write the chemical equation, what we are doing is creating something that is a representation of its energy as well as its balanced chemical equation. So if we look at here where we have the combustion of octane, okay, 2 moles of octane reacts with 25 moles of oxygen to produce 16 moles of CO2 and 18 H2O. The delta H here is reported as minus 10,928 kilojoules per mole. Okay, so, but the catch is, if you have a look at octane here, it's 5450. Okay, so 5450 is actually half of this, and that is what we're given as the heat of combustion. Okay, but the catch is it's for 1 mole of fuel, and in this equation we are told that we burnt 2 moles of fuel. So what we've done is taken the delta HC value and multiplied by 2 for the 2 moles that were burnt. And in a thermochemical equation, that's what we do. We need to consider the coefficient of the fuel and then look at the delta HC per mole and therefore write it for the right amount. Okay, so because delta HC in our tables is produced per mole, if the coefficient of the fuel is anything other than 1, then we need to multiply by that amount to get the delta H value that we report as our thermochemical equation. Okay, so thermochemical equations are balanced chemical equations where we include the delta H value for that equation. Okay, so in this case, the heat of combustion of the fuel is 10,928 divided by 2, okay, which is what we saw on the table of values and what would be reported in your data booklet. So if we want to work out the exact amount of energy given off by a chemical reaction, then we need some way to measure that. And as we said, we can't measure enthalpy directly. We can only measure it using the change in temperature of the surroundings from which the energy is entering into. So if you remember, we had Q is equal to MC delta T, allows us to work out the amount of heat energy given off into a solution. Okay, so we can say that the energy of a combustion reaction, the total energy of combustion reaction, is going to be the number of mole of fuel that is burnt multiplied by the energy per mole, the heat of combustion. Okay, so that gives us the exact amount of energy that we would expect to see. Okay, so if we look at 5.40 kilograms of propane, C3H8 as our formula, it's going to be burnt in unlimited oxygen, so this is telling us that combustion is complete. Looking at this equation, if we're going to calculate the energy released, it's going to equal the number of mole. So I'm going to substitute in my equation for mole, which is the number of mole divided by the molar mass. So, and remembering that this must be converted to grams. So I'm going to get 540. Need an extra zero, 5,400 grams divided by, this is going to be 3 times 12 plus 8, so this is going to be 3644, and then multiplied by the delta HC of propane, which of course we can get from the table we saw just before. So that would be 2,220 kilojoules per mole for propane. So we get our 5,400 divided by 44, then multiply that by 2,220, and we will get 27,2454. Actually, that's 272,454. Now, this is going to be, we've worked out from this 5.4 kilograms of propane. So we've got to pay careful attention to units here. This was in kilojoules per mole. So this is actually going to be kilojoules. So we could actually convert this into 273 megajoules, taking it up another factor. Okay, so that's looking at how much based on the heat of combustion from a table. We can also do this experimentally, which we call simple calorimetry. So this is similar to the experiment that you observed for the endo and exothermic reactions. So we can measure the heat of combustion of a reaction using a very simple apparatus, essentially a spirit burner that allows us to burn the fuel, which is what this is here, a spirit burner. And then we can burn it under a conductive can. Okay, this one is copper. And it has a known sample or known mass of water inside. And then we can measure the initial temperature and the final temperature of the water, and therefore work out how much energy passed into the water and work out how much that therefore was given off by the combustion of fuel. So this is what it generally looks like. Okay, it's a very simple reaction, and we will actually look at doing this reaction soon, okay, or this experiment. So you place your fuel into the spirit burner, it has a wick, it burns. This is a reflective shield, which is one of the ways that you can actually improve the results you get from this. You have a thermometer, and of course another way that you can improve your results is by having a lid, and I want you to think about why that might be. So we can take that idea, so this is a simple calorimeter for a heat of combustion. Okay, clearly we've got to be able to burn the fuel. We can also do this for reactions by taking an insulated vessel or a calorimeter, placing in a thermometer and a stirrer, and then we run the reaction inside the solution inside this. Okay, so we can have an ampule, or we'll basically start the reaction off in here, have the temperature before the reaction starts, and then the temperature after the reaction has gone to completion, and this is referred to as a solution calorimeter. So essentially what we're doing in calorimetry is we are trying to measure how much energy is going into our solution, okay, be it water from a heat of combustion reaction or the solution that the reaction is occurring in itself, which means that we want to make sure our system is insulated so that we can minimize the heat loss to the surroundings, or if it's endothermic heat entering, okay, from the environment. We want to put a lid on it to minimize heat loss. So if we're heating something up, we of course can have heat escaping out into the cooler environment, whereas a lid will keep that in. Okay, we need to have a known volume of water and reactant at the beginning and the end. So because remember, we're going to use M of the solution in order to work out our final Q value. So we need to know that accurately, and we need to know the temperature of the water at the beginning and the end, because we're going to use the change in temperature in order to work this out. Once we have all these, we can work out the energy that was emitted during the combustion reaction or the exothermic or endothermic reaction. This method does still have limitations, okay, and if you think about it, these are the same limitations that would have been observed in the reactions that we looked at in the endo and exothermic experiment. So I want you to think about these, take some notes, and we will discuss them further in class. The other thing to be aware of is units. As we saw there, we could convert into megajoules if we're getting into very large amounts of energy. This is particularly important when we're talking about the production of energy on a societal scale, so the burning of diesel or coal for the production of electricity, or the amount of energy that we need to put out in order to make our cars drive and things like that. Typically though, in chemistry, we will see the units of kilojoules per mole. Okay, we tend to see kilojoules per gram if we're talking about a mixture. So petroleum fuel or something like that will often be given as a mixture. So here's an example problem that I would like you to have a go at, and then the solution is produced on the next slide. I'm not going to talk you through the solution, but I will point out that here is your mass of the spirit burner and the mass after burning. Okay, so this is the mass of the spirit burner and the fuel before anything was burnt, and then this was after. So you're going to determine the mass of fuel that was burnt from this. This is your initial and final temperature, so you'll use delta T here. And then this is the volume of water that was in the can. And remember that the density of water is given as 1 gram per centimeter cubed. So you can get the mass that we use in this calculation from here. Okay, so once you determine the heat energy change, so we're going to determine Q using Q equals mc delta T, okay, then you can determine the heat of combustion of methanol. So the amount of energy that was given off per mole for methanol, okay? So we're going to take the amount of energy that we found and divide by the number of mole. The solution is laid out for you on the next slide, so have a go at it and then make sure that you come back and check your solution. Okay, once we have figured out what our theoretical value is, we need to compare it back to the theoretical value. This is the value that we would get from the data booklet, okay, from your tables in your data booklet, and we would compare it to our experimental value. And as you can see here, this is quite a bit different to what we got from the data that we were provided. When we do this, we then have opportunities to discuss experimental error and what that means for our results. If you think about all the errors that we've talked about in class in regards to these types of reactions, you can or should be able to give a reason for your discrepancy. Okay, many of these are going to include loss of heat to the environment, maybe incomplete combustion, absorption of the heat energy by the apparatus and not taking account for that in our calculations. Okay, so we're going to have loss of heat to the surroundings. The can, clamp, other things may have absorbed some heat. Okay, and other equipment. The thermometer, metal clamp would also absorb some of the heat from this. So that's it for our introduction into basic calorimetry. Of course, we'll do some more practice calculations in class. Hopefully, you are starting to put together all this stuff from energetics, and I'll see you next time.